Well, everyone's joined. I'd like to welcome you all for coming today to our second workshop in the How to Prove workshop series. Bienvenidos a todos. Gracias por venir al segundo taller de nuestro ciclo de talleres de demostraciones. Le cedo la palabra a John Skukalek, que se encargará del taller el día de hoy.
Ya, gracias, Adrian. Bienvenidos a todos. A ver, me dicen que puedo presentar en inglés, entonces I'm going to switch over to English now. Bueno, por si acaso, si tienen preguntas en español, I'll do my best to understand and answer them, okay? All right, can I share my screen? Let's see here. Okay, tell me if you can see that. Can you guys see that? Awesome. Okay, so I'm going to talk to you guys today about proofs. Now, I'm not really going to tell you how to prove things or how to get good at proving things. I mean, how do you get good at anything in life? Like piano, for example. My daughter was just having her piano class. Hay que practicar, right? So you have to do it. Hay que hacerlo. Manos a la obra. So I can't really teach you how to prove things, but I can tell you a little bit about, well, as my title says here, what's behind a proof, okay? So I'm going to begin with an innocent question. Sounds innocent, okay? So something that I think everybody here knows very well. Why is the product of two negative numbers positive? Okay. Well, you know that this is true, but do you know why? So we have to begin by, I mean, like if somebody came up to you and asked you why this is true. In fact, it's one of those things that I've heard people who don't study math like ask about. You know, like, okay, I understand, fine, the product of two positive numbers is positive. Like, eso sí tiene sentido. Okay, fine. But what about the product of two negative numbers? I mean, how do you, like, why? Like, why is that? Okay, so that's the first thing is, yeah, we do have to accept something. We're going to accept that the product of two positive numbers is positive. Sin justificar. We're not going to justify that at all, okay? So, well, when you want to prove things in mathematics, you have to be aware of what things mean, what words mean, okay? So you have to know what we even mean by a negative number, okay? So let's say, as you know, that it's a number A, but maybe you didn't at first think of it this way. It's a number A such that minus A is positive, which already I've seen cause some initial confusion with students. Like, just because I call it minus A, but doesn't that mean it's a negative number? I see the minus. No, not necessarily. Okay, so let's take two numbers, A and B, such that minus A and minus B are positive. So we are led to this question: what can we say about the product minus A minus B, minus A times minus B? And I know you know what it is, or you think you know what it is. In fact, maybe you think that, okay, ya entiendo, it is done, the proof is done, because I know what that is. You probably want to propose that minus A times minus B equals A times B, don't you? Okay, you can propose that if you want. But, I mean, these questions just keep leading to more questions. So why is this true? Why is minus A times minus B equal to A times B? So that's what we have to prove. In fact, if you were paying attention, you'll see that that answers the question. Okay. Well, now the question is, what does minus a actually mean? I mean, here we really need a definition. Okay, math is full of definitions. So what's the definition of minus a? And you probably know as well, it's the number with a certain property. So it's the number that when you add that number to a, you get 0, right? Okay, so what's 0? Well, you also know that 0 is a number that has a certain property. So when you add anything to 0, nothing happens. It's the same number. So you see how I emphasize this for all here? Para todos. So this is very important. This also brings up a question, which actually is part of the proof that we're thinking about. How unique is 0? Like, can you have more than one number 0 that plays the role of the number 0, that acts like the number 0? If you stop to think about it, the answer is no. It's very unique. Because look, if 0 prime has the same property that I said that 0 above does, well then just think about it. 0 plus 0 prime and 0 prime plus 0 are simultaneously equal to 0 and to 0 prime. What? Well, just think about it, okay? There's a related question that's also very important. So how unique is the number minus a? Notice we write it as minus a, like we have the a as part of the notation. That suggests that it only depends on a. To each number a, we can associate a unique number called minus a. There's kind of a function going on here. That's probably the last time I'll use the word function. Okay. So is it uniquely determined by a, as the notation suggests? Well, once again, it is. And you know it is. Actually, here's a more general question. This actually happens all the time in proofs. That it's funny, you want to prove something, it's sometimes easier to think about something more general. It's just weird how it works that way. So like trying to solve a more general problem actually makes understanding the original problem easier. So you've seen this. If you have a plus b equal to a plus c, well, you know that you can just, oh, what's the word we use? I try to avoid this word. I don't like it. Cancelar, right? You can cancel the a, get rid of it. Se va. Okay, but why? Yeah, this is the so-called cancellation property of addition. All right, so let's prove that. Okay. So if you have a number d such that d plus a is 0, well, then you can take the equation a plus b and a plus c, and you can add d. I mean, we do this all the time in algebra. We add a number to both sides of the equation or whatever. Already right here, what you want to do next, and I know that you know what to do next, but you can only do this if you assume that addition is associative. So you know the parentheses, you have to be able to move them around. Well, let's assume that, okay? So we can use the associative property of addition, and then we get 0 plus b equals 0 plus c, so therefore b equals c. You've seen things like this before. It's not anything new, I don't think. Okay, but remember we were trying to think about minus a times minus b equals a times b. Okay, so now we know that minus a is unique in the sense that it solo depende de a, it only depends on the number a. This is important, okay? Because you probably, when you're looking at this equation we want to prove that you know is true, you probably want to say, oh, well, it's because minus a times b, for example, here's a separate thing. Forget about the two minuses. If I just had minus a times b, well, I know that that's the same as minus a times b, right? Well, if you want to prove that, you have to know what it means, okay? So we have to show that by definition of the number minus AB, that it's the number that now we know is unique, that when you add it to AB, you get 0. If we want to know that the number minus A times B has this property that you see written there. That's the definition of minus AB. Oh, okay. Que intenso, no? So here's another thing we need that you've seen before, so it shouldn't shock you. We need the distributive property of addition and multiplication. In fact, starting with the above sum, you might say we want to factor, right? But that factoring really is thanks to the distributive property. We're going to factor out this B, and then you get A plus minus A. Oh, and that's 0, so I get 0 times B. Great news. But what is 0 times B? Oh, it's 0. No surprise there. But this is a really interesting point in our so-called proof, because we ask ourselves, do we have to assume this? Or do we have to prove it? You actually don't have to assume this. You can prove it. I'm not going to prove it. You might say this is the first exercise if you want exercises. You can prove it using the properties of numbers mentioned so far. In fact, muchos de ustedes, many of you know that in the course of Cálculo para Ciencias that you guys have to take with me, we proved this on the first day of class. In fact, many of these things here, you will probably, my students from calculus will be like, yeah, I know that, John. Okay, but don't worry, there will be some stuff, some new stuff for you later on. So you can prove this. Do it if you want. Okay, thus, if this is true, we know that minus A times B is equal to minus AB. Well, in the same way, if we had A times minus some number, we can also put the minus outside. Actually, this uses a slightly different version of the distributive property. I'll just leave that there for you to think about. Finally, we get that minus A times minus B is this. So we get minus AB. So we've applied the minus thing 2 times. Wait, is this really A times B? Something else to prove? Well, yes, but it's basically by definition. Just think about it. This is true. So we did it. Okay, so that's why the product of 2 negative numbers is positive. Are you satisfied? So notice that when we proved this thing, there were certain things that we had to assume without proof. This is just the way mathematics works. You can't prove everything. Okay. So here's the things we assumed. Briefly here, we have this associative property. We have the definition of 0. We have the definition of minus a number, or additive inverses. And we have these 2 distributive properties. But just notice that there are also some things about numbers that we didn't even need to assume. Like, for example, we never assumed that multiplication is associative. You know it's supposed to be. We didn't even assume that addition and multiplication are commutative. Didn't have to. Also, we said nothing about the number 1. In fact, back when you saw minus A, maybe you thought you were clever. And you would say, hey, but isn't that minus 1 times A? Well, it is, but I didn't even introduce the number 1, and therefore, what's minus 1? Anyways, you've seen. We assume nothing about multiplicative inverses as well. If you have a non-zero number it has an inverse in this sense. These are all things that you've seen about numbers, nothing new. I'll give you some fancy terminology though to go along with these things that you already know. So all of these properties, the ones we used, I hope I didn't miss any. All the ones that we used in our proof and the ones we didn't even use. If you put them all together, you get the properties of what's called a field. En español se dice cuerpo, no se dice campo. In algebra, se dice cuerpo. Okay. Something else, though. I mean, our question was about positive and negative numbers. So this is the notion of an order. So one way to define an order is you have a subset of your field with the following properties. And if you think of positive numbers, you also know this already, that if you have in fact, I'll just refer to the elements of P as positive, okay? That's going to be just a definition. So this says that every element of F is either positive or negative or zero, and it can't be multiple of those. That's what the first two say, in fact. Also, the sum and product of positive elements is positive. Fine. Okay. Now we define negative to mean that minus. So A is negative if minus A is in P. Again, if you've studied calculus with me, when we use the book of Spivak, you have to get used to thinking this way, and it kind of blows your mind at first. Okay. And then order refers to this. A is less than B by definition if B minus A is positive. Okay, so what did we prove? I mean, in fancy terminology, what we proved is that in any ordered field F, the product of two negative elements is positive. And as you see, no es tan simple. You have to use lots of the rules very carefully. Here's a corollary that you're familiar with. So in any ordered field, is this blocking your view here? This little guy here? What happens if then it minimizes it. Okay, hold on, sorry. So in any ordered field, the square of each non-zero element is positive because, a square means something times itself. So in particular, that's positive if it's non-zero, if you think about it. So a square can never be negative. That sounds familiar with things that you've heard about. Okay, so let's talk about the square root of 2. This is another thing that everyone's heard of, that the square root of 2 is irrational. Okay, it's just like, well, yeah, of course. And you may have even seen the proof. For example, in my class, you guys saw the proof. But just like we did before, like, what does this really mean? And and maybe the proof actually involves some unexpected things. Well, there's a lot right here that I'm not going to go into detail about, okay? The natural numbers are the positive integers. So n is the natural number, z is all integers, positive, negative, or 0. And we have the good old rational numbers that can be written as a over b, where a and b are integers, b is not 0. But then there's this goofy thing that you have to learn about, where two fractions can actually be the same number. Notice that so a over b is equal to c over d. We define it in terms of something we already know, the integers. So it's when a times d, assuming I wrote it correctly, yeah, a times d equals b times c. All right, many of you guys have seen this before. Let's explore what happens if we suppose there exist two natural numbers. If you think about it, it's okay to assume that a and b are positive if we're going to do this, such that a over b squared is 2. Notice that this is really a statement about integers, that a squared is 2b squared. So if you've seen the proof before, you know that this is what you have to think about. So it involves the concept of even integers. So an integer is even if it's equal to 2 times another integer. So the question becomes, as we'll see, I mean, so notice that it says that a squared is even. What does that let us say about a? And again, you probably know the answer. We can say that a must also be even, but why? How do you actually prove that? Or just like, you just accept it like, ah, yes, sí tiene sentido. No, we can prove it, okay? In fact, here is something important. To say how I wrote this, that a squared is even implies that a is even. It's the same thing to prove that if a is not even, then a squared is not even. Why is it the same? You have to just think about it. Well, actually, it's logic, okay? But there's no magic here, it's just logic. This is what's called the contrapositive of the statement. So I won't get too deep into logic, but if P implies Q, so the statement P implies Q, oh, I missed a word here. The statement P implies Q, what was I trying to say? Oh, I'm sorry. The contrapositive of the statement P implies Q is not Q implies not P. We say the two statements are logically equivalent. All I'm going to tell you about that is meditate on it. I like to tell my students to meditate on it until it makes sense, because it's supposed to, because it's logic. So the question becomes, what can we say about a number that is not even? And you say, once again, oh, I know what to do. I know what that means. But I'll tell you, this is where things get tricky. This always happens in math. Things are always trickier than they seem. So an integer that is not even must be equal to an even integer plus 1. And as you know, such integers are said to be odd, impar. Even is par, odd is impar. Now, this is not, maybe you know this, but this is not obvious. Okay, so it turns out that therefore every integer is even or odd, but the proof is not so trivial. And I'll leave this as another exercise for you. Maybe you've done this exercise before. This relies on what's called the principle of mathematical induction, which says, briefly, we don't need to go into this. I'm not here to talk like this. If A is a set of natural numbers that contains 1 and also contains n plus 1 whenever it contains n, then A equals n. If you've never seen that before, well, you can think about it. But you need that to prove that every integer is even or odd. And here's the part that's simple, though. Luckily, some parts are difficult, some parts are simple. It's simple to check that if A is odd, then A squared is odd. It's just a little calculation. In fact, more generally, if A and B are odd, then the product is odd. In fact, I think that's an if and only if statement, if you know what I mean by that. I'll leave that to you as well. Okay, so yeah, many of you have seen this proof. We don't need to spend too much time on it. So if C, then A squared equal to 2B squared implies that 2C squared equals B squared. What happened? We multiplied by 1/2. So what happens is, just like we saw with A squared and B squared, B must be even. So we showed that A and B have to both be even. If you let B equal 2D, then we get this. Okay, here's the point. In fact, we're done. Guess, look at that, we're done. Thus, there cannot exist an element of Q whose square is 2. And you say, okay. So, okay, why? I'm kind of like kidding you, because you really have to think about this, all right? The first thing is this what's called a proof by contradiction. And this is nothing special. This is just something that we get to do in math, because what happens is, in math, if you have a statement, it's either true or false. It can't be both. So we build mathematics assuming that things are true or false. I will mention, though, that logicians have put this into question, the truth of that. Just a mysterious comment. Okay, more logic. This is the last of the logical stuff, I think. Here's some more logic for you. Think about this. If you want to prove Q, so you have you want to show that some stuff implies Q. For example, if you want to show that, well, as I'll say in a minute, you want to prove Q. So what if you knew that if P is true and Q is false, that implies that P is false? Well, guess what? If you can do that, you just prove that Q is true. Because this strange looking thing is the same as P implies Q, if you think about it. But this is proof by contradiction, actually. So it's really just a term for how the logic is being used. Okay, enough about that. What is the contradiction in our proof? So basically, if A over B squared is 2, then you can always find, oh, and I was supposed to say here, C is less than A and D is less than B. Está al revés. Then you can find a smaller A and B that still work. But you can just keep doing that over and over again. And this sounds wrong, but what exactly is wrong? This creates a non-empty subset of n with no smallest element. There's something called the well-ordering principle that says that that's impossible. And maybe your intuition tells you that that's impossible. But in fact, the well-ordering principle can be proved using using the principle of mathematical induction, which maybe some of you guys have thought about in my class. But in fact, it also implies it. The two statements are logically equivalent. So Fermat, who you may have heard of, he had a very dramatic term for proofs like this. He called it a proof by infinite descent. Because you just keep finding, it's like, just gets smaller and smaller, it just keeps going forever, and I don't know, the universe explodes or something. But really, it's just contradicting the well-ordering principle. All right. Oh, it also, another way to say it, usually I say it this way when I explain it, is that it contradicts the more down-to-earth fact that every rational number can be expressed in lowest terms. Basically, where A and B are relatively prime, if you know what that means. And that's actually an important point, is that there's more than one way of thinking of what the contradiction is. And that's just the way math works too. There's not only one way to understand a proof. There usually are many ways. Let's keep talking about the square root of 2. So does it exist? Well, you've heard about it, right? You've heard about raíz de dos, right? As if it's just this thing. Okay, so here's the thing. Q is the most well-known ordered field that I defined for you earlier. We actually just proved this theorem. There does not exist an element of Q, this very special ordered field, whose square is 2. But you could think about other ordered fields. So can you find a different ordered field where there is something like the square root of 2? I mean, just notice that 2 means 1 plus 1, and our ordered field definitely has something called 1 by definition. And it's actually not difficult. Now, maybe you don't know what this means yet. Some of my students do. I'll just mention this quickly. So the integers modulo p, where p is a prime number, gotta love prime numbers, they form a field with p elements that's called ZP. And all I want to point out, if you don't know what this means, is that you can have fields that only have finitely many elements, but it has to be a prime number of elements. Kind of mysterious. So for example, the number that works here is 7. 7 is the magic number, the lucky number, because 3 squared is 9, which is 7 plus 2. So if you know what I mean by the integers modulo 7, that's why 2 has a square root in the field with 7 elements, C7. Okay, moving on. I don't need to spend too much time on that. Oh gosh, I say that and then I realize that I keep going deeper. Okay, if you want to know, as some of you do, if you've ever studied number theory, you might know that 2 has a square root in ZP if and only if p plus 1 or p minus 1 is divisible by 8. Kind of weird. So Gauss, the famous Gauss, studied what are called quadratic residues. So you can look it up on Wikipedia if you want, quadratic residues. Okay, enough of that. Here's the thing though, a finite field can never be ordered. And that the proof is extremely short. It's like just a few words, which I won't say. I'll leave that to you. An ordered field has to have infinitely many elements. But in fact, here is an infinite example. So it's not difficult to find an infinite field where 2 has a square root. Take Q2, so ordered pairs of rational numbers, add them like this is like vector addition, if you know what that is. But check out this multiplication. You have AC plus 2BD, and then AD plus BC. This might look familiar to you, but I won't say why. Now, the element 1, 0 is a multiplicative identity you can check. And if you square 0, 1, you get 2, 0, which is 1, 0 plus 1, 0. So, and you can check that this really, so 0, 1 plays the role of the square root of 2 in this field. And it really is a field. You can take that as an exercise too if you want. Actually, this field can be ordered, but it's not immediately clear how to do so. I'm not going to discuss how to do so, but actually it's related to everything else I'm going to talk about. Here's another approach. This is going to connect with some other things in mathematics that you already know or that you think you already know, okay? So what about the order will guarantee that the square root of 2 will exist? And the answer has to do with upper bounds. So quickly here, in fact, that has to do with least upper bounds. So let me just say this again. The point here is not all the mathematics I'm throwing at you. It's to think about the big picture. So an ordered field is said to be complete if every non-empty subset that has an upper bound has a least upper bound. So we denote the least upper bound of A by sup A, or it's called the supremum of A. In fact, it's totally equivalent to assume the same thing, but for lower bound, greatest lower bound, and what's called the infimum of A. Here's the thing. I could write this all out in its glorious detail, but I'm not going to do it. It's actually what you would expect if you know what an upper bound of a set of numbers is. It's the least upper bound. Least is el más pequeño, right? So you can write it out if you want. But here's something that can be proved, and I'll give you a hint how to prove it. If you have a complete ordered field, and you take the set of elements whose square is less than 2, then you have found a square root of 2, because the supremum of A, which by assumption exists, the square will be equal to 2. I won't prove this, but I'll give you a small, actually I couldn't decide to call this a small hint or a big hint. It's small in the sense that it's very short, but this is the key to everything. If you have, and some of my students might recognize this problem, in fact, I'm not even gonna tell you, the hint is just to consider this, it's just a hint, okay? I'm gonna tell you exactly what to do. So if you have 2 numbers, A and B, let's say 2 positive integers, you can consider, sorry, if this is blocking your view, can you see that? I think if I don't click, it goes away. Am I right? There we go. Just repeatedly consider the number A plus 2B divided by AB. I will say nothing more. Let me ask you this though. Given that theorem, which is an interesting theorem, like what did we really prove very much? Like for example, if you wanted to I almost thought about writing this theorem, the square root of 2 exists. Did we really prove? I mean, does this theorem here really prove that the square root of 2 exists? Well, I mean, not really. It tells you that in any complete ordered field that the square root of 2 exists. But there's a big gap here, un hueco gigante. How do we even know if we're going to, have this stuff? It's kind of silly if we can't even show that a complete ordered field exists. Like, an example, please? So we didn't actually prove that there exists a complete ordered field. Okay, so this is where things get difficult. Well, if they already were difficult, then they get even more difficult. They get quite difficult here. But this is something you know. There does exist a complete ordered field, and it's known as the field of real numbers, R. Everybody's heard about real numbers. Los números reales. Yeah, sure. But how do we know this? Well, because we can prove it. How do we prove it? Well, this is the strange thing that nobody ever really thinks about. You actually have to define the real numbers. They often use the word construct, which means you have to define it, but you got to do requiere mucho trabajo. Okay, and then once you define it, you have to prove it's a complete ordered field. So here's the good news, though, is that, I mean, everything that we've done, that's been done up to this point, gets to be used. I mean, in math, you don't just start from scratch. You always you use all the other things that you've proved. I mean, that's a good lesson for proofs, is you always have to use the things that have already been proven. If you forget what they are, then you might just get stuck. So in this case, the good news is that we get to start with Q, which we already know is an ordered field. In fact, what we have to do, we have to do this if you think about it, you have to put Q inside R. There's actually a little theorem here. If you have any ordered field, it contains inside of it like a copy of Q, if you think about it, because you can just take 1 and you can keep adding 1, and then you can divide by something else where you keep adding 1. There was a word. There's a word for that I'm going to use. I wasn't sure if I use it now or if I use it later. I use it later. So I mean, that's the thing, is it gives us motivation for what we're supposed to do. We start with Q, and we have to extend it to this complete ordered field. Okay. So how do you do this? This is something that is pretty complicated, actually. So I don't think many of you guys have seen this in any of my classes. Maybe you will by the end of your studies, though. So there are 2 popular approaches to constructing R from Q. Okay, so I'll just quickly tell you. It's a little bit of interesting mathematical history. The first one uses what are called Koshi sequences. Actually, now my students of Cálculo para Ciencias 2, they've heard the term Koshi sequences. So actually, this I don't even know about this. I say due to Agustin Louis Koshi ? Because honestly, I don't know, and I couldn't find this. You might have to ask a mathematical historian about this. I don't really know. So they're called Koshi sequences, probably because Koshi did important work related to this. But I don't think this construction of R from Q is attributed to Koshi. It's not like he necessarily proved it. Probably mathematicians used some of his ideas to prove this. So as you see here, Koshi died in 1857. Why am I telling you that? It's because the other popular approach uses what are called Dedicant cuts. due to, this one for sure is due to Richard Dedicant. And I didn't know this, I had to look it up. He published a paper about them in 1872. So they're called Dedicant cuts. He probably just called them cuts. And we call them Dedicant cuts because he's the one who introduced them. And that's officially in a paper from 1872. So if Koshi died in 1857, then, well, that's the confusing thing, is which one came first. So like I don't even, like, who really proved the real numbers exist? Like, who was the first person? I don't think it's as simple as that. But definitely Dedicant came along and published a really beautiful paper that I'll tell you a tiny bit about how this works, how Dedicant cuts work, okay? Okay, but this is I'm sort of trolling you, if you know what I mean with this here. A Dedicant cut is a non-empty proper subset alpha of Q such that if alpha is less than B and B is an alpha, then A is an alpha. And if A is an alpha, then there exists B and alpha such that A is less than B. Got that? That's the thing. Math is when it's hard to absorb in your brain. You know, it's like, what does it mean to actually understand this? Well, if you sit down and think about it, you'll understand it. First, you have to memorize it. I can add some words here. You have a subset of Q. The first thing I mentioned here says that whenever, so basically the set goes to minus infinity, that whenever it contains an element, it contains all, whenever it contains a number, it contains all smaller numbers. But then the weird part is the other one. It says that if it contains an element, actually say it this way, it does not contain a maximum element. Which maybe at first that sounds weird to you, but if you think about it, it's easy to find sets of rational numbers that que no tienen un elemento máximo. Simplemente no existe. Oh, in fact, I'm going to give you an example, but I got that because, yeah, if this is the first time you've seen this, you're like, what? But don't worry about it. But here's the Dedicant cut, okay, if you really want to understand this. If you take a rational number, say A, what if you just take the set of rational numbers that are less than A? Well, you can check that that's a Dedicant cut. And I mean, in particular, it does not have a largest element. Trust me. Okay. Notice it does not contain A. If it contained A, then that changes it completely. But here's the mysterious thing. And if you think about it, I mean, this is the whole point, that not all Dedicant cuts are of this form. So they're not all given by just choosing a rational number and then taking all numbers less than it. For example, does this look familiar to you? If you take the set of rational numbers whose square is less than 2, it's not of this form. Now, there's something to prove there. You're going to need to use the fact that you can never make the square of a rational number equal to 2. So you can check that it is a Dedicant cut if you look carefully at that strange definition. And that gives you a hint at what's going on here. So what you can do is you can define R, which sounds so weird, to define the set of real numbers. So what is a real number according to Dedicant's approach? It is a Dedicant cut. I mean, what I want you to take from this is that math is just full of definitions. So it is possible to actually define a real number in this way. So R will be the set of all Dedicant cuts. So as we just said, I don't like the word obvious to use too much, but maybe to say the more obvious than the other Dedicant cuts. If you take a rational, then we have associated with it the Dedicant cut that consists of all rationals that are less than that rational, A. What that actually does is it puts, as I mentioned before, a copy of Q inside of R. But we have to identify, we have to say, okay, we're going to think of those obvious Dedicant cuts as the rational numbers. So you get Q inside of R, but Q is not equal to R because of these strange Dedicant cuts, like this one that has x squared less than 2. All right. I'll tell you briefly how R works if you find this interesting. In fact, this is the thing. When you, in mathematics, when you come up with the right definitions for things, things just fall into place. Like all the pieces just come together. So, I mean, it's another thing. How was Dedekind smart enough to think of this? Well, that's a separate thing. Like, how do you develop the intuition for this or the idea? That's much more difficult. So, if you have alpha and beta in R, which now I'm telling you that they're Dedicant cuts, and they're not equal, which means they're not equal as sets. Now, you can just define the order to be, so to say that alpha is less than beta, if there's nothing complicated here, if alpha is a subset of beta, it's just, you find these things that is like just so simple that you know you're onto something. And here is the big thing. Remember, we needed a complete ordered field. So how does the supremum work? If you're going to show that this is a complete ordered field, that we have the least upper bounds always exist, well, you have to find them. So you have to say what it is. Well, now there's a simple way to do that, because so if you have a subset of R, so it's a set of sets, it's a set of Dedicant cuts. It's not empty, and it's bounded above with respect to what I just said up here about subsets. The supremum just becomes the union of all those sets. So here I wrote U of A. If you just take all the sets and you put them all together. Now you have to check, for example, that union is a Dedicant cut, and then that Dedicant cut really is the least upper bound of A. Now you can do that if you want. In fact, this part I'm not going to do at all. Now you need to define addition and multiplication in R. And then you need to check that it's an ordered field. So remember, we already have addition and multiplication defined on the rationals, let's say, but we have to extend it to R. Well, I'll leave that. That's a mate. So to make those definitions and check that it's an ordered field, I'll call that a mega exercise. And I'll leave that to you if you want. But keep this in mind that we're trying to extend. And again, we have to use what we already know. So we have to extend the addition and multiplication that's already defined on Q to R. So if you think about that, that'll give you guidance for what to do. In fact, the fancy way of saying is that Q, it becomes an ordered subfield of R. So yeah, there exists a complete ordered field. It's a theorem, it's true, that there exists a complete ordered field. And therefore, as we discussed earlier, it must contain the square root of 2. And there are tons of other numbers that you've heard about that such a complete ordered field has to contain. In fact, this sort of brings up a question. I mean, you've heard all about the real numbers, perhaps. I'm telling you some things about them as well. How unique is R? In fact, I mean, going back to what I told you about the two approaches to defining the real numbers. Well, they're completely different. I didn't tell you anything about the Koshi sequence approach. You can look it up if you want. So there are two approaches to defining the same thing. What does that actually mean? Well, it's defining they're both approaches to defining a complete ordered field. Well, that brings up the question about uniqueness of complete ordered fields. So the answer is that the R is as unique as can be, that's very important here. Not only does R exist, it's unique. But what does that mean exactly? I'll just leave this as a statement that you can look up the meaning of, or you can even define if you know what's going on. So you can prove that any two complete ordered fields are isomorphic. That's a fancy word for that they really are the same. So even if they look different on the outside, inside they're the same. So using multiplication and addition and the order, that they behave the same way. And you can prove it, okay? In fact, that's probably easier than proving that R exists, as proving that it's unique. But you have to know you have to know what all the words mean. Okay, so I added this slide at the end because I didn't want to just be like, okay, that's it. All right, so the moral of this story, okay? So what am I'm not really trying to teach you mathematics so much as teach you about mathematics. One thing that I always tell my students is that, I'll say it in Spanish just for fun. No es tan necesario saber cómo demostrar todo, pero lo que sí es importante es saber si algo que se puede demostrar es muy difícil demostrar o es fácil demostrar. Okay, let me, so with that in mind, I'll just read this to you, what I wrote, okay? So mathematical truths are only true subject to the assumptions that we make, or in more fancy terminology, the axioms that we use. If you change the axioms, then it's like you change the rules of the game. A lot of people think that in mathematics, it's like you're figuring out what's true, the secret truths of the universe. I don't think it's exactly like that. I mean, truth in mathematics is not set in stone. Something that is true with respect to one set of axioms, like our axioms of an ordered field, they can be false with respect to another set of axioms. Mathematical proofs, and thus mathematical truths themselves, are usually more complicated than they seem, as hopefully you saw as we were discussing these things. Even proving something simple as the sounds as simple as the product of two negative numbers is positive really involves and really involves a lot. All right, guys. Gracias por escucharme. Si tienen alguna pregunta, con gusto te voy a intentar contestar. Any questions? You can ask in English or in Spanish.
John.
Thank you, John.
No, thank you, guys.
Gracias, John.
Estuvo súper wow, o sea, en verdad es súper un montón de información que hay que procesarla, pero wow.
Okay, bueno, me alegro mucho. I'm glad you enjoyed it. I was worried that it was way too long, as I kept thinking of more and more things to say. But when I realized that I could put together these slides, that helps you move like a lot more quickly. So I know I probably overwhelmed you with too many things, but that was sort of the point, was to show you that some of these things in mathematics, they're really, really complicated. Like, let me say this, a bit of advice is when you're trying to, because I loved this thing when I was a student. I just loved the fact that whenever there was anything I had a doubt about in mathematics, I could check if it's true or false. Sometimes that was really difficult, but it was comforting to know, well, let me see, is it true? I mean, if I do this and I'm not sure. but I at least knew that it wasn't just like I have to accept it just because somebody told me to accept it. So I encourage you that in all of your classes, and really in everything, question everything. But especially to get, to succeed in the mathematics major, you really have to, everything that you write, everything you do, you really have to question. You have to question your own work if you're writing a proof. And by the way, all of mathematics is proofs. It's not like there's proof, there's mathematics with proofs and mathematics without proofs. No, everything is with proofs, but it can get very difficult. So try to make sure, question everything in your proofs, and because you can always dig deeper and ask why things are true. Don't just, if you're not sure about something, don't just move on and say, oh, I hope that John, if you're in my class, that John accepts this as true. Question it, figure it out. Anything? If you have questions about the mathematics that I introduced, I'd be happy to go into more detail if you'd like. ¿Alguien? ¿Alguna pregunta?
O sea, yo creo que todo quedó, o sea, bueno, yo sí tengo full preguntas, pero bueno, ya nada, o sea, ya ahí tocaré ir viendo con el tiempo, pero, o sea, no, o sea, quedó muy claro, o sea, el hecho de como la trayectoria que se debe utilizar y como que, o sea, que debemos cuestionarnos en sí por qué son así las cosas, o sea, igual lo que dijo de los números reales y todo lo demás, entonces, ajá, o sea, creo que eso queda muy claro.
Chévere. Sí, una cosa es que, por ejemplo, en matemáticas no creo que es tan importante pensar muy rápido. Entonces, yo nunca pude pensar muy rápido y resolver problemas de una manera muy rápida. Siempre pensaba despacio, pero muy profundo. Y creo que, bueno, para mí es más útil poder pensar profundo en lugar de rápido.
Hay una cosa que me, o sea, gustó full. Alguna vez leí justamente una prueba de que 1 más 1 es igual a 2. Obviamente parece muy obvio, pero usando matemática súper formal se vuelve súper bonito una demostración así.
Pero no escuché la última parte, Daniel. Mi audio se fue un ratito. Says my
No, que,
connection
o
is
sea, no era,
unstable. Sorry. Perdón.
no era
Sí,
pregunta.
entonces, en Q, 1 más 1 es igual a 2. Y de hecho, en otros ordered fields, 1 más 1, sí, bueno, pues siempre podemos decir que 1 más 1 es 2. Lo que pasa es a veces 2 es, por ejemplo, 2 puede ser igual a 0 también. Por ejemplo, en el cuerpo Z2. So, I mean, the thing is that we say words, but you just have to know what those words mean. Like, if I tell you 1 plus 1 might not be 2, you're like, oh, well, you just don't freak out. Just think about, I mean, you have to hear more. You have to know exactly what you're saying. I mean, the thing is, once you understand what all the words mean, then once you understand it, it's like, yeah, bien. Bueno, ya entiendo. But before you know what all the words mean, things are very confusing.
John, and when
Yeah,
will
Diana.
we see how to construct R in real analysis?
It's a really good question. Yeah, you know what? I didn't even see this when I was a student. Oh, that could be because I remember there was a class I didn't take because I got credit for, and I got to skip Real Analysis 1. I remember when I was an undergrad. So maybe they talked about it in there. I think they did. That's why I didn't get to see it. So yes, not until real analysis will I tell you guys. In fact, basically you'll tell yourselves about it. The book we read, it's a famous book by Rudin, but this is good for you to hear as well. Even most books on real analysis just get to the point that here are the rules of the real numbers. Now let's prove things with them. The actual construction of the real numbers, I find it really interesting, but some people would say es más parte de la lógica que análisis. But nevertheless, I find it very interesting. Maybe other people are just like, yeah, whatever. I want to get to, the important things. But so what I was going to say was the book we use in real analysis is a famous book by Rudin. Even he does include it as like an appendix, I think, in the first chapter. But even he says, bueno, está aquí. Basically, he's like, sí pueden ver si quieren, pero no es tan importante. So, but when in real analysis, we will have a chance to discuss it. Yeah, but before then, it never actually comes up. See, it's so weird because this is one of the things I was going to say earlier, was that imagine if there was more than one complete ordered field, then you could have like two different types of calculus, which is just weird. It's almost like mathematicians knew all along that calculus is this unique thing. But it wasn't until much later that people actually put that on a logical foundation. It's so weird to think about if you could have two different styles. And actually you can, there are other types of calculus, but what I mean is something that's similar, it's really close to calculus that we know, but not quite the same. That would be weird, but that doesn't happen. But it's something you can read about. I actually found the paper from Dedicant. I think it was translated to English. I found the PDF because I think it was originally in German. So yeah, you can look up the paper if you want, or you can. There's tons of places you can read about it if you find it interesting.
And in this Rudin book, the way he constructs art is like with these Dedicant cuts, or like with the Koshi sequence?
Yes, that's also a really good question. Rudin mentions, and I think this wasn't even in the original book, he added it in a later edition. He has a section on Dedicant cuts. I remember the first time I taught real analysis, I taught from a book that David borrowed from me. David Ervas borrowed from me, and I think he still has it, where they use Koshi sequences. And in that first time, I did talk about how to do it with Koshi sequences. What's really neat is when you see it both ways. Oh, and by the way, in our topology class, we'll kind of talk about it. The Koshi sequence approach. So actually, I should have said that earlier. We kind of will see it in topology, but it's not really defining. Well, it's related, but it's not exactly the same thing. So we will see Koshi sequences in topology, but Rudin uses the Dedicant cut approach. And what's neat is when you understand both of them, and you see that the point is, it's not like it's defining things in mathematics is not like you have to. There's only one way to do it. There are so many ways to do it. So many ways to learn mathematics and to develop mathematics. So it's you learn that you can do the same thing but in completely different ways. Should stop sharing this so I can see. Nobody's got their hands up or anything. Is there anything else that you guys would like to talk about?
It's just amazing how mathematics comes all together to construct and to be like constructive. It's like the building blocks of what we know. And
Yeah, it really is. And the interesting thing about what always fascinated me about all this business with the real numbers is calculus, that all you guys learn, even engineers learn calculus. It only exists, it only works because of some of these deep theorems that I was talking about today. But Newton and Leibniz obviously did not know about these theorems, but they were able to develop calculus with their intuition that it should work. But mathematicians much later, like for example, introducing the epsilon delta definition of a limit, that was one thing. But then imagine trying to actually define the real numbers. I mean, Newton and Leibniz were probably just, didn't even occur to them that that was something you had to do. Just like, well, yeah, you got a line, you got all the points, and okay, yeah, there should be a square root of 2 in there somewhere, right? I mean, for example, I was going to talk about geometry today, but I decided not to because I don't understand geometry well enough. But geometry tells us that the square root of 2 should exist. So they use their intuition to do all these things that, like, imagine if there was like a huge logical problem with all of this, and with the whole proof by contradiction thing. What if people just kept proving theorems, and then there was, oh my gosh, algo está mal. We have these two things that contradict each other. What that would mean, for example, that if you had done everything correctly, it would mean that there does, for example, maybe it could mean that there does not exist a complete ordered field, and so everything is just throw it in the garbage. But it's crazy because calculus is even used in physics, and like many things in the real world function thanks to calculus. Airplanes fly because engineers know how to use calculus and things like that. So the world works. But imagine if there were some big logical problems. Well, in a sense, there are big logical problems, because look at how difficult it is to define all these things. But it can be done, luckily.
Do you think that maybe we could be missing something in our set of things that we're assuming to prove?
Yeah. You know what I was going to say? I think I thought of this right as you were saying this. We were thinking along the same line here, that we have all of those axioms of the real numbers, which doesn't show that they exist, but they do. So we just start with these axioms. How do we know, for example, that you can't prove some of the axioms using the other axioms? For example, there was a famous thing in geometry about this that you've probably heard of, the parallel postulate. Geometers thought that they could prove that if you have a line and a point not on the line, and it seems like there exists a unique line that goes through the point off the line, but doesn't intersect the other line. And we know that's a parallel line. So that seemed so clear to them that they wanted that to be a theorem. They wanted to prove that. So sure, they had other rules of geometry, but they tried to, I don't know a lot about it, but I think they tried to prove the parallel postulate. Pero no se puede demostrar. And in fact, how do you know that you can't prove the parallel postulate? Is because there exists non-Euclidean geometry. There exists geometry where all the other rules of geometry, for example, on a sphere, you can have geometry where the parallel postulate is false. But they just weren't thinking that way. So it also made me think that with the real numbers, like if you take away, the following should be true, that if you take away one of the axioms of the real numbers, then there should exist a mathematical object that has all the properties except that one. Like, for example, you take away the complete part. Well, that's easy. We know that's the rationals. They are an ordered field. They're not complete. But it was weird to me. I was thinking about this. What if you take away some of the other rules of the real numbers? What are some examples of things that satisfy all the rules except for that one? Because presumably you can't prove any of the rules using the others, because mathematicians would have figured that out. And then, like, for example, what I told you guys, any number times 0 is 0. But you don't have to assume that. You can prove that. So we don't need to put that in the list of, in the definition. Yeah, I mean, that's the thing, is that when you prove things in mathematics, I think a lot of people don't understand this. When you prove things in mathematics, you're only showing que son consecuencias lógicas de las reglas, the axioms. Nada más. It's not like you're proving that it's some kind of universal truth. It's how do I say it? Sujeta a esas cosas que asumimos sin demostrar. So truth is still, even in mathematics, truth is still kind of relative. If people think that mathematics is like absolute truth, I don't think it's useful to think of it that way. Like, that's what got the people who were thinking about the parallel postulate into trouble, is because they weren't thinking. They were thinking that this is some universal truth. We should be able to prove it. Well, you can only prove things based on what you're willing to assume.
John.
See.
And I read that in set theory, there's this thing.
Hey, it's Juan. Hey, Juan. Why didn't you're not taking my Advanced Calculus 2 class this semester? I miss you. It's nice to hear from you again. I'm sorry for interrupting you. It was nice to hear you again.
Yeah,
Go ahead.
It was such a cool talk. I
Thank you very much, Juan.
A bit jealous of students in calculus too. Yeah,
I'm glad to hear that. I hope you are.
What books do you use in the class?
So we use Spivak? Sure. Well, okay, so only in the beginning we use Spivak. Ya acabamos con Spivak. So we only use Spivak for like the first 3 weeks. And then we switch to a book, which also David Hervas has my copy of this book. But did I show you? I feel like maybe some students last semester asked me about what we were using. It's called Vector Calculus. If you want to send me an email, if you want to know, Juan, Cálculo para Ciencias 2, básicamente, so basically it's sequences in series plus Cálculo 3, the regular Cálculo 3, pero de una forma un poco más fuerte. So, yeah.
Y bueno, podemos seguir conversando, pero para de una vez parar la grabación, como que vamos a hacer el cierre oficial. Entonces, gracias a todos por venir. Thanks, John, for your presentation.
Thank you, guys. It's very fun to talk to you all.